Okay, welcome back everyone to section 7.1. So we've done a couple examples in this video series for finding the Laplace transform of some basic functions like constants, polynomials, trig, exponentials. So we kind of have a couple transforms in our toolbox already. So what I want to do is sort of summarize what we've found so far so that it makes it a little easier for us to use in the future and to note that these are repeatable. So, let's summarize our common Laplace transforms of functions. So, we could make a table like f of t, okay, and the Laplace transforms we've done so far. So, we've done one, we've done, a polynomial like t to the n. This could be for like n equals 1, 2, 3, etc. So t squared, t cubed. We've also looked at exponentials, so like we could say in general e to the at. We've looked at sine of 2t, so we could say like sine of at. And so we don't have to go out and find cosine, we'll say like cosine of at. And then one thing we haven't found yet is natural log, but I want to make a note of that in this table. So um, let's go ahead and write down what these general Laplace transforms would be of these functions. So the constant one that we saw is 1 over s. Okay. And for a polynomial like t squared, t cubed, what that actually is would be n factorial over s to the n plus 1. Okay, and if you're a little unfamiliar with factorial, like 2 factorial is just like 2 times 1. 4 factorial is like 4 times 3 times 2 times 1. So it's multiplying all the previous terms together. That's what factorial means. Um, so, that's the kind of form that it has. Exponentials that we saw, what this turns into is 1 over s minus that term a. Okay, sine of at that we saw, that's the form a over s squared plus a squared. And cosine, which we didn't see, but I want to define now to have ready for us, is s squared plus a squared. And this is another one we didn't find, natural log of a of t. What's the Laplace of that? Don't worry, it does not exist. Okay, so a couple things, factorial, that's the exclamation point. But yeah, so got a couple tools in our box already. And I want to use some of these to apply the linearity concept of Laplace transforms that we were kind of discussing in the beginning of this section, so that we could use a linear combination of Laplaces to solve these individually. So linearity of Laplace transforms. So let's look at the Laplace of 1 plus 5t. We haven't really done an expression with multiple terms yet, but because of that linearity property, what we could do is actually split this up into Laplace of 1 plus the Laplace of 5t. Okay, and we could even take this a step further in that we can take out the 5, the constant, and just have the Laplace t. Well, we know what that is already. We found that already. We know what the Laplace of 1 is already. So this, using our table as well, like, the Laplace of 1 is just 1 over s. The Laplace of t to the first power would just be like, this form right here. And so what I would have is 1 over s plus 5 times 1 over s squared. Okay, so y1 over s squared, we actually found this out, but yeah, let's using this form like t to the n, that's like t to the first power. So that's like, you know, 1 factorial over s to the 1 plus 1. So that's just 1 over s squared. So that's kind of where we're getting that from. Just so you're sure what how we got 1 over s squared using the table, but we found it earlier through all the hard work. But yeah, so our final answer is 1 over s plus 5 over s squared. And just a couple of things to keep track of. S needs to be greater than 0, which we found in our work. Um, and it's just what we need to account for. So let's go ahead and check out example B now. So Laplace of e to the 5t minus 10 sine of 2t. Pretty uh, hard to look at if we try to tackle this in one Laplace, but yeah, we can use our linearity principle and split these up. So 4e to the 5t minus the Laplace, or maybe let's take it a little step further. We'll say plus the Laplace of negative 10 sine of 2t. Okay, our linearity property lets us take out the constant. So 4 times the Laplace of e to the 5t plus, or now it could be minus 10 times the Laplace of sine of 2t. Okay, so we're going to use, you know, the table for, say for exponential, e to the at is 1 over s minus a. So the Laplace of e to the 5t would be 1 over s minus 5. So this would be 4 times 1 over s minus 5. And the Laplace of sine of 2t would be a over s squared plus a squared. So this would be 2 over s squared plus 2 squared. So minus 10 times, 2 over s squared plus 2 squared. The key indicator is whatever these are, a. And so we could simplify this, this turns into like 4 over s minus 5 minus 20 over s squared plus 4. Okay, and that's our Laplace transform using the linearity property. All right, so let's look at this last one. Um, Laplace of 20e to the negative 3t plus 17 minus 9. You guessed it, we're going to use that linearity property. So, we could separate this out into Laplace of 20e to the negative 3t plus the Laplace of 7t plus the Laplace of negative 9. And we could take out all of these constants. So this could be like 20 times the Laplace of e to the negative 3t plus 7 times the Laplace of t minus 9 times the Laplace of just 1. And yeah, we just use a table. Um, we have e to the negative 3t. So if you come up to our table, okay, so this is like, a is negative 3 here. So this is like 1 over s minus negative 3. So this would become, you know, 20 times 1 over s minus negative 3 plus 7 times t. We know what that is. That's just like 1 over s squared minus 9 times the Laplace of 1, which we know is just like 1 over s. And so our final answer is like 20 over s plus 3 plus 7 over s squared minus 9 over s. Okay, so that is a good couple examples of using the linearity property to make the Laplace transform way easier for us, all right? And when you're doing these, go back to the table, okay? It gives you some basics for now and saves you a little bit of a headache when you try and solve these, all right? But that's it for this video. Thank you for watching, and then we'll see you in the next example. All right, take care.